situations when this is obviously a function of time, and this is 1 over radians, which is going to be 2 pi f, where f is frequency. And we talk about frequency typically as hertz. All right, we can also do Fourier transforms over space. And I'll call this kx x dx, where this is now called the wave number, angular, I guess. Angular because it's like omega number in x. And it will have dimensions radians. And if we write kx as 2 pi, let's say kappa x, kappa has units of 1 over distance. So this kind of tells you how the domains, time and frequency, are inverted from each other. The scales are actually, time goes to 1 over time. Okay? Space goes to 1 over space in the opposite domain. Okay, we talked also about the discrete Fourier transform, the digital Fourier transform. And we gave a definition. Obviously, we have to have bounds. Gk e to the minus I 2 pi over n jk, where gk is basically a series of numbers. I'm just going to start it at 1. And the distance between these numbers we'll just call delta g. That's the sampling interval. Notice that we don't need to know what the sampling interval is for the discrete Fourier transform. We'll call this g, and what's the subscript there? Is it j? Is it k? Anybody? Okay. Right? So if we're looking back at this equation, actually it should be j here. My apologies. And this is backwards from what we had the last time. Oh, I'm sorry. Backwards. K, j. Right? We're summing over k, which is our time axis, and our result is in the frequency domain. So this is frequency, and this is time. Okay, let's take a simple example of that, kind of like we did last time. And then we'll look at a few graphical Fourier transform pairs. So let's say that this is our time function, g1, g2. It's a vector of values in time. And g1 might look like this. Let's say something like this. Now for grins, and let's say that my transform is g1, gn. So in this case, each of the values of g transforms into a value of g. But notice that in general, and typically cosine of 2 pi over n jk minus I sine 2 pi over n jk. All right? And then we can split this up into two separate sums. So I'm only going to look at the first term right now in deriving this matrix. So I'm just going to put a cosine next to each of these numbers, just to designate that I'm not worried about the full transform. I'm just worried about the first term right now, just for demonstration purposes. All right? So this transform is going to be sum of k equals 1 to n gk cosine 2 pi over n jk. And this is going to be gk cosine. This is known as the cosine transform, which is part of the Fourier transform. And notice that it is real. We don't have to worry about imaginary numbers in the cosine transform. Okay, let us go to the first term. Okay, the first term is j equals 0. Actually, it's j equals 1. I'm going to change this just so that I get the term that I want. Okay, and I'll get this to n minus 1. Okay, so the first term is j equals 0. So, yeah? No. This is the k index, this is the j index. So this is j equals, let's call it delta t. J equals, delta f. J equals 2 delta f. All the way down to j equals n minus 1 delta f. Remember, j is frequency and k is time. Okay, so for the 0th frequency, what I've got to do is I've got to multiply e to the minus, well, actually, cosine of 2 pi n 0k. So what's cosine of 0? Cosine of 0 is 1 everywhere. So, like I was showing last time, I get a whole bunch of 1s there. Okay? And if I have a whole bunch of 1s, what I've got for the 0th frequency is I've got g0 plus g1 all the way up to plus gn. So this is equal to n times the average of g. Right? So the very first term, the 0th frequency of the discrete Fourier transform is simply the average value. Okay, what about when j equals delta f? Let's say delta f equals 1 for Grimm's. All right? Well then, what do we have? We have cosine